The first case we'll look at is where material 1 is a perfect dielectric, so there's no conduction in a perfect dielectric, so the conductivity of material 1 will be 0, and material 2 will be a perfect conductor. So in a perfect conductor, the conductivity goes to infinity. Going to our expression for the intrinsic impedance, for a perfect dielectric, sigma is 0, so the intrinsic impedance in material 1 is the square root of the ratios of the permeability to the permittivity in material 1. So the intrinsic impedance in material 1 is a real number. In material 2, the conductivity goes to infinity, so the intrinsic impedance will go to 0 in material 2. Substituting the intrinsic impedances for the two materials in our equations for the reflection and transmission coefficients, we see that the reflection coefficient is -1 and the transmission coefficient is 0. So our electromagnetic wave will be completely reflected by the perfect conductor. This also explains why if you look at a polished piece of metal, you see your reflection. This case is essentially a mirror. Since there's no transmitted wave, the electric and magnetic fields in material 2 will be 0. Let's look at the electric and magnetic fields in material 1. If we put in our parameters for material 1 with sigma equal to 0, we see that the propagation constant is an imaginary number, so there is no attenuation constant. So we have the sum of our incident and reflected waves, and so our gamma becomes just J beta. And since our reflection coefficient is -1, we can substitute for the amplitude of the reflected wave minus the amplitude of the incident wave. So now let's take our phasor form of our electric field intensity, multiply by e to the j omega t, and take the real part. So when we do that, we get this result, which are two contrapropagating waves, or incident and reflected wave, and we see that they have the same amplitudes. We will use these two trig identities to rewrite these two cosine terms, which I've done here, and the end result is this for the electric field intensity in material 1. This result is something called a standing wave. Whenever you have two contrapropagating waves of the same amplitude, the result is a standing wave. There is no energy being transferred because you have the same amount of energy propagating in the plus z direction as you do in the minus z direction. An animation really helps to develop a mental representation for a standing wave due to two contrapropagating waves. This website had a great animation, but it no longer exists. But someone made a YouTube video of that animation, and if you go to this link, or maybe easier, go to YouTube and search for formation of standing wave on reflection and find this YouTube video and run that video. It's an animation with an incident wave and then eventually a reflected wave, and you can see how the standing wave develops. Here is a depiction of the electric field intensity for our standing wave at different times. So at any z location, the electromagnetic wave is oscillating with the frequency omega. So at this point it would be oscillating up and down like this, at this point like this, and at this point it will always be 0. This term determines that amplitude as a function of z. So there will be z locations where the amplitudes are 0. Amplitudes of 0 occur whenever sine of beta 1z is 0, and that's when beta 1z is some integer multiple of pi radians. So the amplitude is 0 when beta 1z is equal to minus n pi, where n takes on the integer values 0, 1, 2, 3, etc. Substituting 2 pi over lambda 1 for beta sub 1, we can solve for the values of z when the amplitude is 0. And that occurs when z is minus some integer multiple of lambda 1 over 2. So when n is 0, z is 0. When n is 1, z is minus lambda 1 over 2. So here's our next amplitude of 0. When n is equal to 2, z is equal to minus lambda 1. So that's our next amplitude of 0, and so forth. We can now find the magnetic field intensity in material 1 by adding the incident magnetic field intensity with the reflected magnetic field intensity. We will also use the reflection coefficient of minus 1 to rewrite minus E sub R0 as E sub I0. We will take this expression, multiply by e to the j omega t, and take the real part, and we get the magnetic field intensity is 2 contrapropagating plane waves of the same amplitude. Going through the same procedure, we get the standing wave pattern for our magnetic field intensity. In this figure, we have plots of the electric field intensity and the magnetic field intensity at various times. We can see that there's a quarter wavelength shift along the z-axis for the locations of the 0 amplitudes for the electric and magnetic field intensities.